As we'll see in the next few lectures, the climate system is a complex interaction between the sun, the Earth's atmosphere, the Earth's hydrosphere, the biosphere, and even the lithosphere. That's summarized here in this pretty cool diagram, which shows the uplift of moisture-laden air in the troposphere. This moisture-laden air eventually is going to cool until water vapor condenses and falls as rain. Also depicted here is a warm band of equatorial Pacific water that we know as El Nino. We can see desert areas like the Atacama here that are deserts because the prevailing winds hit the Andes and squeegee that moisture out. Here, more locally, I used this image from just a couple weeks ago to torment my friends back in Ohio who were complaining about the temperature dropping into the 20s, plus 20s Fahrenheit, which would be, say, -4, -5 centigrade here. And we hit some catastrophically icy cold temperatures when it comes to wind chill during this period of time. Those of you that live in Saskatoon know what I'm talking about. A little further south, where people don't know as much about cold weather, there's one thing that's in the news every day. It's, other than Cardi B, Kim Kardashian, Justin Bieber, Tiger Woods, other than those people, in the news every day is weather. Just recently, as in last week, Texas experienced a crash. Their grid shut down. And the reason their grid shut down completely is it's their grid. It's the only state in the continental U.S. that has its own energy grid. And they cheaped out on it, and the result was they lost power. In Australia last year and into 2019, the devastating bushfires killed an estimated 1.5 billion animals. And you may remember some images like these of koalas being rescued by firemen, kangaroos that perished caught up in fences. This led to a near extinction event, a functional extinction event for koalas. At least that was the initial report. There are enough koalas in zoos around the world that they're not going to go extinct. But for other animals like the dunnart, it is very likely that this species went extinct. And there's a number of other species that are living right on the edge. It's been estimated that 1.5 billion animals, mammals, birds, reptiles in the continent of Australia have perished during these fires. A lot of these animals are found nowhere else on Earth. They were either killed outright or they've been affected by destruction of their ecosystem. Manu Saunders, a research fellow and insect ecologist at the University of New England, said, "We're not just talking about koalas. We're talking mammals, birds, plants, fungi, insects, other invertebrates, amphibians, bacteria, and microorganisms that are critical to these systems. Individual animals might survive, but when their habitat is gone, it doesn't matter. They'll die anyway." And although dead and scorched koalas and kangaroos became the symbol of wildlife suffering in the worst blazes to ever hit Australia, conservationists note that these species are not at the greatest risk for extinction. Of greater ecological concern are the unusual, the strange animals that could disappear from a continent with the world's highest rate of mammal extinction. One thing people don't talk about are insect extinctions. These insects are the foundation of a living forest. They make up half of all the animal biomass and are a major food source for virtually anything that moves. Bugs also break down organic matter and help pollinate plants. Inside branches, under leaves, within hollowed logs, and in pockets in the ground, tens of millions of bugs are being burned alive. Some may vanish without ever being discovered. Only about 20 or 30% of Australia's insects are known to science. Climate change, invasive species, overuse of farm chemicals, and human development threatening insects, the fires could be the last straw that drives fragile populations over the edge to extinction. And extinction is forever, at least now. In China, we have an example here of a curtailment in emissions. Once the COVID-19 virus hit in a big way and China locked down its population, shutting down most industry, you can see a dramatic cleanup of the air, a huge reduction in emissions in March compared to January. And this persisted for several months after this. In India, the skies became clear. So pre-COVID sky versus COVID sky, pre-COVID sky versus COVID sky. This is the result of a curtailment of the use of burning coal and wood, as well as other pollutants from cars and trucks and so on. So the air cleaned up a little bit. But climate change has not stopped for COVID-19. Atmospheric CO2 concentrations showed no signs of peaking and have continued to increase to new records. Lockdown-related falls in emissions will not reduce CO2 concentrations. Global fossil CO2 emissions rose 62% between 1990 and 2019. The average global temperature for 2016 to 2020 is expected to be the warmest on record, about 1.1 degrees centigrade above the 1850 to 1900 average. Human-induced climate change, also called global warming, is affecting life-sustaining systems, from the tops of mountains to the depths of the oceans, leading to an acceleration in sea level rise that's going to have cascading effects for ecosystems and human security. Climate change impacts are most felt through changing hydrological conditions, including changes in snow and ice dynamics. By the year 2050, the number of people at risk of floods will increase from its current level of 1.2 billion to 1.6 billion people that are at risk for flooding. The study of Earth's climate system is crucial to the well-being of life on Earth. That includes our lives as well. Consequences of climate change include global warming, sea level rise, and unfavorable changes in weather patterns. These might be more frequent droughts, more frequent flooding, more intense flooding, more snow, more wind, less wind, higher temperatures, lower temperatures. All these things are a component of models that look into the future using our current greenhouse gas emissions. So in this lecture, we're going to talk about components of the climate system, the greenhouse effect, what is it and what isn't it, climate variation, the carbon cycle, and 20th century warming. This will introduce us to anthropogenic global change. Now, components of the climate system include definition of climate. This is very important. You should know this. It will be on the exam. Climate describes the average surface conditions and their variation during daily, yearly, and long-term cycles of solar heating. All meteorological statistics for a given area over a 30-year period of time. Climate is not average weather, it's not average temperature, it's not average height or weight, it's not average cost of a car. All meteorological statistics for a given area over a 30-year period. Every time it was windy or not windy, rainy or dry, snowy, sleety, haily, all of these things are components of the meteorological database, and they're all part of climate. The climate system includes all parts of the Earth system and all of the interactions in space and time. Gaining a better understanding of the Earth's climate system is critical to all aspects of life on Earth. Everything on Earth, on the surface of the Earth, is influenced by the Earth's climate system. Cyclical changes in the amount of input of solar radiation, which we call insolation, are known as solar forcing. The sun is forcing our climate system. The main components of the climate system are the atmosphere, hydrosphere, cryosphere, lithosphere, and the biosphere. In the simplest scenario, breaking things down into two primary components. One, the climate system involves the transfer of energy from the sun to the Earth's atmosphere and from the Earth's atmosphere back to space. That's the solar-Earth interaction. Once the energy joins the Earth system, becomes part of the Earth system, we monitor the way that energy moves around within and transfers between the ocean and atmosphere, principally. So it all starts with the sun. Here we have a diagram illustrating that. The sun provides the energy to the atmosphere. The atmosphere has a certain chemistry. It's made up mostly of nitrogen, a significant amount of oxygen, about 1% argon, 1 to 4% water vapor, a little bit of carbon dioxide, and little bits of other greenhouse gases. The way these interact with this radiation determines how much heat is reflected, how much is stored, and that determines the function of the climate system. Now, the cryosphere is going to consist of the ice. Cryo means ice, so it's the ice sphere. It consists of valley glaciers, snow cover, like we have here on the ground in Saskatoon right now, continental glaciers, which cover large areas, and sea ice, which covers a different amount of ocean surface at different times of the year. Then we have volcanism. Volcanism supplies greenhouse gases to the atmosphere. This magma chamber is going to interact with the material that's subducted, and not in this diagram. That subducted material gets cooked, and we juice out the greenhouse gases like CO2, a small amount of methane, sulfur dioxide. These things enter the atmosphere, they interact with the atmosphere, and they change the behavior of the atmosphere. The biosphere does something similar. It takes in carbon dioxide, produces organic matter that gets cycled through different plants and animals, and then it gets kicked back into the atmosphere as CO2 or methane usually. Lakes and rivers supply nutrients back and forth between spheres that are going to change the health or productivity of the biosphere. Then we have everything humans are up to. We tear down the biosphere, we put in big industrial farms, we burn fossil fuels, we change the sea level, we change the atmosphere, we do a lot of damage. And we'll talk about that more later in the course. The hydrosphere, dominantly the ocean, but also all fresh water that we find on land and in the ground. And then the lithosphere. It acts slowly but relentlessly. When discussing the Earth's climate system, the first thing we generally consider are the atmospheric zones, the layers of the atmosphere. Starting at the Earth's surface, moving upward, we encounter the troposphere. Above the troposphere, we pass through the tropopause into the stratosphere. Above the stratosphere, we pass through the stratopause into the outer atmosphere. The troposphere is the lowest layer of the Earth's atmosphere. It's also where nearly all weather conditions take place. It contains 75% of the atmosphere's mass and about 99% of the total mass of water vapor and aerosols in the atmosphere as a whole. The average height of the troposphere is 18 kilometers, or 59,000 feet in the tropics. It's much thicker there, thinning to about 6 kilometers, or 3.5 miles of thickness, 20,000 feet in the polar regions in the wintertime, where it's thinnest. The lowest part of the troposphere, where friction with the Earth's surface increases airflow, is known as the planetary boundary layer. This layer is typically a couple hundred meters thick to 2 kilometers in thickness, or a little over a mile, depending on the landform and the time of day. This is what you can see commonly in video of climbers on Everest. They're in the boundary layer. In that boundary layer, because it's in the jet stream as well, they're susceptible to being blown off into the comb. Atop the troposphere is the tropopause, the border between the trophosphere and the stratosphere. The tropopause is an inversion layer where the air temperature ceases to decrease with height and remains constant through its thickness, more or less. The word troposphere itself is derived from the Greek tropos, meaning to turn toward, or to change, or turn over, and sphere, as in the sphere of the Earth. This reflects the fact that the rotational turbulent mixing plays an important role in the troposphere's structure and behavior. Most of the phenomena we observe as day-to-day weather occurs in this layer, in this sphere, in this shell. Above the troposphere is the tropopause. For our purposes, the tropopause is the boundary in the Earth's atmosphere between the troposphere and the stratosphere. More officially, it's a thermodynamic gradient stratification layer, marking the end of the troposphere. According to the World Meteorological Organization, the tropopause is the boundary between the troposphere and the stratosphere, where an abrupt change in lapse rate usually occurs. It's defined as the lowest level at which the lapse rate decreases to 2 degrees per kilometer or less, provided that the average lapse rate between this level and all higher levels within 2 kilometers does not exceed 2 degrees per kilometer. Going upward from the surface, it is the point where air ceases to cool with height and becomes almost completely dry. More formally, the tropopause is the region of the atmosphere where the environmental lapse rate changes from positive, as it behaves in the troposphere, to the stratospheric negative behavior. So going upward from the surface, it's the point where air ceases to cool with height, as we can see here. So in the troposphere, the turning over layer is where we fly. We fly right at the top of the troposphere. And the reason we fly right at the top of the troposphere is because it doesn't overturn. This overturning can be felt on flights when they just hand you a full cup of hot coffee and boom, the turbulent tone comes on and it starts to splash all over the place. The coffee is usually handed to you here in the middle of the troposphere, and you finish it as you reach the smooth, non-turbulent layer of the upper troposphere. Now, the composition of the atmosphere, like the behavior of the atmosphere, also changes with height. In general, air is composed of nitrogen, about 78% by volume, about 21% by volume oxygen, and a little bit of argon, about 1% argon, 420 parts per million carbon dioxide, a widely variable amount of water vapor, a widely variable amount of ozone, and a little bit of methane, etc. The atmosphere is the most mobile and rapidly changing part of the climate system. 75% of it is in the layer closest to the Earth, known as the Trophosphere, which is, as we saw, about 11 kilometers thick. The Trophosphere mixes vigorously because of differences in density. This is due to heat and water. Water vapor can make up to several percent of the atmosphere, with most of it within or near the tropics. The stratosphere extends from about 11 kilometers to 50 kilometers above the Earth's surface. Beyond that, the atmosphere gradually dissipates into space. There's no clear boundary. Water vapor occurs in highly variable amounts in the atmosphere. It usually makes up about 1% of the atmosphere, but it can be as high as 4% in the tropics. Now, ozone is an important trace gas for its role in greenhouse warming and as protection from UV radiation. Just recently, we saw a split in the stratosphere because of ozone. Most of the ozone is found in the ozone layer 25 to 30 kilometers above the Earth's surface, which we can see here. So we have ozone near the Earth's surface as a result of pollution and those air cleaning devices you can buy online or in your local store. As we rise in the atmosphere, ozone decreases until we reach the ozone layer. This is where ozone is good for you. Ozone is good for you here in the ozone layer. It's bad for you down here where you live.